Hello, and welcome to another lecture from my class, PSYC 440/640. The class that's called Experimental Methods, but it's really more of a class about univariate data analysis techniques, especially hypothesis testing, but also some other stuff like the construction of good graphs and confidence intervals, which we'll be touching on today. Anyway, as I often do, I'm beginning with a comic, which as you can see here is from phdcomics.com. This is one of those ones that seems to never really go out of style. As you, I'm sure, are aware, various sources in the media, whether they're news sources or bloggers or just people who have Twitter feeds, can easily misuse statistics. And gosh, sometimes it seems like part of the job that I have as a teacher in statistics is just helping my students, helping myself really, to just avoid being misled by, well, confusing and deliberately misused statistics. Anyway, something to think about. And speaking of stuff to think about, in this class we're going to be talking about bias and assumptions, but if you flash back to the last lecture, you'll know that I kind of stopped almost halfway through a discussion of confidence intervals. So as you'll see in just a few more slides when I set out the outline for the class, we'll be talking first about things like confidence intervals, but we'll eventually get to this topic of bias and assumptions, and I will start that conversation or start that topic in this lecture and finish it in my next lecture. So again, what we'll be covering today, a little bit more about confidence intervals, and then we'll be moving on to talk about estimation and bias, things like outliers, assumptions, and so on. Okay, just to warm yourself up, last time I talked a lot about power analysis. Here is a graph from G-Power, of course, looking at a simple one-tailed t-test. And I've got some different regions of the graph labeled A, B, C, D. Practice or test your understanding by trying to name the labeled elements in this figure. Okay, I'm pausing here to let you do that or let you check your notes. Hopefully you can do this. If you can't, go back and check my last lecture or fiddle around with G-Power, and hopefully this will help sort of get your understanding solidified or crystallized and help you get ready for more topics we're going to cover today. So moving on, where we left off last time, we were using the Counseling Center dataset, which I've used quite a bit in past lectures. And of course, if you're enrolled in my class, you have access to this dataset through Blackboard. If you're not, you can probably just follow along pretty well. And I talked a little bit about the idea of sampling data from a population and computing statistics, whether they are means for different groups, people who got treatment or people who did not, whether they're test statistics like t-statistics and so on. And I talked about the idea that you could, in principle, do this repeatedly over time and construct a sampling distribution for whatever those statistics are, or whatever that statistic is, whether it's a mean or a t-statistic or whatever else. And you could describe the nature of that sampling distribution, and depending on the sizes of the samples you're drawing, that sampling distribution would be relatively narrow and well-behaved, or relatively dispersed and perhaps not very well-behaved, and so on and so on. And about the time I left off, you were probably wondering, or you might have been wondering, what's any of this have to do with confidence intervals? Well, that's where I want to get to next. In order to get there, I want to quickly go back to the idea of z-scores, and I'm pretty sure I've introduced these in previous lectures, and if not, this is a concept that you've almost certainly encountered in any basic statistics class, z-scores. Now, really quickly here, I want to make the point that z-scores are not the same thing as z-test statistics, although these are sometimes confused by people. Here we're talking about z-scores, which are just distances from the mean expressed in standard deviations, or what's called sometimes standard normal deviates. So for instance, if you had a particular outcome variable y, you could, for each person in your data set, compute a z-score for that person on the outcome variable y by taking his or her individual score, subtracting from it the mean, and dividing by the standard deviation. And as you probably know, these resulting scores, these z-scores, has some attractive features. For instance, they have a mean of 0 and they have a standard deviation of 1, just simply as a consequence of how they are computed. Moreover, if the distribution of values is normal in shape, like you can see here in this image, then we have a sense of where different percentages of all the cases lie with respect to their z-scores. So for instance, we know that roughly 34.13% of all cases lie between the mean and plus 1 standard deviation, and so on and so on and so on. And if you want to take cumulative probabilities, you could say, well, about 95% of all cases lie between about negative standard 2 standard deviations or 2 z-score and positive 2 standard deviations or 2 z-score. So just to kind of be a little bit more explicit about what I just said, if you have a set of data which are transformed into z-scores, then, and if you know that the data is normally distributed in your sample, or you have reason to believe, especially if you have reason to believe the data is normally distributed in the population, you know that 95% of all the values are going to lie between negative 1.96 and positive 1.96. And 99% of all the values are going to lie between negative 2.58 and positive 2.58, and so on and so on. Now those values, or I should say those numbers, particularly the 1.96 number, are important to kind of keep in mind, because as you'll see in just a slide more, they are used in calculations for confidence intervals. So let's imagine that we have gathered a sample of data and run our study, and we're just going to focus on one of the groups right now. Maybe it's the group that got the treatment. We have the mean level of the outcome variable functioning for that group, but we're kind of interested, hopefully, in where the population mean for that variable lies. That is, if we imagine the population of all the people who could have been in the treatment group, what's the mean level in that whole population for functioning? Of course, we can't know that precisely, but we can estimate it based on our sample, and we can estimate it in the following way. First, we begin with that basic formula for the z-score. Then we substitute in those values of positive and negative 1.96 because we want to capture 95% of all the values in the distribution. And we can just kind of rearrange the algebra a little bit like this. And then, because we're not so much talking about a distribution of values of data, but now we're trying to imagine a distribution of values for the mean of all the samples that we could draw if we were repeatedly sampling from this population of folks, and each time computing means. We're now no longer talking about samples of data, we're talking about sampling distribution. We're going to substitute in the standard error for the standard deviation. So instead of having 1.96 times the standard deviation of the distribution, we have 1.96 times the standard error of the sampling distribution, which in this case is the sampling distribution for the mean on the outcome variable. And of course, we can compute, or we can really estimate that sampling error, that standard error by using our formula, standard deviation of the sample divided by square root of the sample size. So we made that substitution there, and now we have the formula that we can use to create the lower and upper boundaries for a 95% confidence interval on our sample mean. Now if we're doing this in Excel, it's actually not very hard, and in class I like to go through this as an example just to show students how this could work. Here I've got my data arranged on the left, as you can obviously see. I've got a little graph area that's going to fill in with values as I make my computations, and I've created a little table kind of towards the center and over to the right that I'm going to use to fill in the various values that I need. So for the treatment group and the control group, I'm first going to begin by counting up the number of cases that we have in each of those groups. Now obviously I could do this just by hand or by eyeballing the data, but I'm using the function count in Excel. So there we go, count those values up. The next thing I want to do is I want to take a look at the minimum and maximum values for those groups. Now this is just something I'm curious about. You don't, strictly speaking, need to have this to make confidence intervals, but I often like to take a look at minimum and maximum values in distributions of data just to get a sense if there are any weird outliers or any unexpectedly high or low cases and so on. And I also like to just practice my Excel skills. So here I'm using the functions min and max, which obviously are giving me the minimum and maximum values of the data in the arrays that I'm inputting there. I'm going ahead and making the average, or finding the mean. That's a function we've used before. And I'm also finding the standard deviation based on a sample, so based on a sample of data drawn from a population. Now to get the standard error, I'm dividing that standard deviation for each group, the standard deviation for the control group, the standard deviation for the treatment group, by, in each case, the square root of the size of that group, which happens to be the same because they're equally sized groups. That gives me the standard error. Now I'm creating a value that I'm just calling error just because I needed to give it a name. Well, actually, I don't suppose I really needed to, but that value is just 1.96 times the standard error for each group, whether it's the treatment group or the control group. And then by adding or subtracting that value, what I'm calling error, from the mean for each group, I can create the upper and lower bounds for the confidence interval for each group, that is for the treatment group and the control group. And because of how I set up my little graphing area in Excel, as I filled in those values, the graph filled in, which, you know, just amuses me and maybe interests or amuses my students when we do it in class. But anyway, as you can see here, we have a bar graph, very simple, representing the mean level of functioning as operationalized by GAF in both our treatment group and control group after our study has been concluded. And we don't just have the means, but we have confidence intervals representing 95, or I'm sorry, we have error bars representing 95% confidence intervals for those means. To be clear, error bars represent a range of confidence around a particular estimate. That range we call the margin of error. So in the case of a 95% confidence interval, what we're reasoning is if we were to repeatedly sample the population and each time compute means and each time compute confidence intervals, 95% of the time the confidence intervals for those means would capture the population mean for the group that we're in the population we're sampling from. So if we're repeatedly drawing samples from the population of all people who can be in treatment, each time we're creating a mean and confidence intervals, 95% of the time that we do that, those confidence intervals will capture the mean. Now, sometime, or 5% of the time over a very long run, we won't. And you can kind of see here an image from Andy Field's textbook where he's showing a sampling distribution. That center of that sampling distribution lines up with the population parameter mean, or mu, and you can see kind of falling down beneath it a series of point estimates for that population mean. So those are the sample means, the little dots. Around each dot is a confidence interval, or a set of confidence intervals, a margin of error, and most of the time that margin of error encloses the population value, but occasionally it doesn't, it misses. To be clear, we almost always do not repeatedly sample the population, repeatedly run our study. We do it just once, and we don't know if we in that just once time got lucky or unlucky, but we reason based on kind of the math and the logic of null hypothesis significance testing that it was probably this time one of those 95 out of 100 times when our margin of error encaptured the population parameter. So we hope that we're one of the lucky times and not one of the unlucky times, although we don't honestly really know for certain. We can't know for certain. I suppose we could construct error bars for a 100% confidence interval, but those error bars would extend from negative infinity in one direction to positive infinity in the other. You know, their margin of error would be the entire number line, and we'd be able to say, well, yeah, we are 100% confident that the population mean lies somewhere from negative infinity to positive infinity. We'd have perfect confidence, perfect certainty, but it would be kind of silly and meaningless. So let's think about something more practical, the 95% confidence interval error bar, something that you've certainly seen and which I've tried to demonstrate just a few slides back. This is just a range, a margin of error in which we expect the population mean to be. Now, error bars that represent confidence intervals have a number of nice features about them, one of which is they just pictographically represent the precision or the confidence we have in estimating the population mean, or whatever the population parameter is, from the sample mean, or whatever the sample statistic is. So for instance, you could slide back or rewind back to the image of my graph a few slides back. You can imagine if the error bars around my graph were very, very wide, what that would suggest to you or to the person reading the paper or looking at the poster is that I don't have a lot of precision in estimating the population value for functioning in my treatment group or the population value for functioning in my control group based on the sample statistics, the means for each of those two groups. In contrast, if those error bars are really, 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 really narrow, it's showing or it's communicating that I do have a lot of precision. I'm saying, yeah, I of course don't know exactly where the population mean is for the treatment group or the population mean is for the control group, but I'm pretty confident it's close to where the sample mean is for my treatment group or the sample mean is for my control group. So to be clear, one thing that's nice about error bars that represent confidence intervals is they give us a way of representing pictographically precision in estimation. Another thing that's nice about them is they allow us to make to draw some simple inferences or test some simple hypotheses. And one of these is one of the ways we can do this is testing the hypothesis that the observed value of let's say the mean of a particular group is different from a predicted value. We might say, is the observed mean of functioning in our treatment group significantly different from 30? Perhaps that's an arbitrary value that we think is important, or 60 or whatever else. If our error bars defined by our if our error bars defined by our confidence intervals overlap with 30, that value, or overlap with 60 if that's our value, then we conclude that we don't have evidence that the population mean is significantly different from 30 or is significantly different from 60. So one thing we can do with confidence intervals is just see whether they overlap a significant or an important value that we want to compare our statistic to. In this lecture I'm focusing so much on means because that I hope makes sense, but in a future lecture I'll talk about making confidence intervals around correlations. And so you might compute a correlation between two variables and you might wonder, is this correlation significantly different from 0? Well, you could test that by making error bars that represent confidence intervals around your correlation and seeing whether that margin of error encloses the value of 0. And if it does, you'd say, well, this correlation isn't significantly different from 0. To flip that around, if it doesn't enclose a value, then you can conclude that your correlation or your mean or whatever it is you've computed is significantly different from that value, at least at a level of type 1 error that corresponds to the confidence interval. So for a 95% confidence interval, you've in a sense conducted a hypothesis test at an alpha level or a type 1 error rate of 0.05. So that's one thing you can do. Another thing you can do is you can look at error bars from different groups. This works best with independent groups. I'll talk about dependent groups later. If those error bars overlap with each other, you could conclude that the groups are not significantly different on whatever variable it is you're measuring. This depends somewhat on the amount of overlap. And the authors Cummings and Finch, in their paper, I think it was 2005, the paper is called Inference by Eye, give some basic guidelines or rules of thumb for interpreting confidence intervals, interpreting error bars based on confidence intervals for independent designs. So designs where the people in the one group are not the same people as the people in the other group. So for instance, their rules of thumb or guidelines are, if the overlap between the error bars representing 95% confidence intervals are a lot, then the groups are not significantly different at an alpha level of 0.05. If the error bars don't overlap, or if they just barely touch, the groups are probably significantly different. And if they overlap only a little, they might be significantly different. And there's a certain amount of sort of guesstimation you would have to do. But as a really simple distillation of these rules, if the error bars overlap a lot, groups are not significantly different. If they don't overlap much or even at all, the groups are significantly different. And that's a handy rule of thumb or idea to keep in mind. So in my example from before, you can see that the error bars here don't overlap, or maybe they ever so slightly touch. It's a little bit hard to see on the screen, but observing this graph, I would conclude that these groups are significantly different in terms of their level of functioning, which I could follow up that by doing like an independent t-test, but I'd essentially be replicating the work that I've done in constructing these confidence intervals. Again, the idea here, or an important idea, is confidence intervals convey information that can be useful, and that information can be used to make inferences or to test hypotheses. Okay, so I hope that all made sense, and at the risk of transitioning too abruptly, I am going to move on. I'm going to talk a little bit about estimation and bias. This is an important, or this is a way of introducing an important set of ideas, which I'll do a little bit in this lecture and a lot more in my next lecture, and which I'll try to return to throughout the rest of the semester. And to get us started, let's just observe, or let's consider that many, if not most, of the statistical procedures that we do in this class involve estimation. By that I mean we're taking information from a sample of data and trying to draw conclusions or make inferences about a population. So kind of like we're talking about with the confidence intervals, we're using information from a sample, the sample mean for a particular group, and trying to estimate the population mean for that group. Now, of course, no model is perfect. No statistical procedure is flawless. There are always going to be mistakes. In this case, errors in estimation. So you can see here a little graph in the bottom of the screen. It represents just a kind of a simple regression that uses the value of the predictor variable x to predict the outcome variable y. The model is that line, and in every case the line misses the data points in the sample of data. That's not a bad thing, that almost inevitably happens, but you can see for each of these individual points we could express the error in the estimation. Now, if we want to get more precise about it, we can remember that error comes in different types or different flavors. And one type of error is unsystematic error, or what we could sometimes call random error. Unsystematic error is called unsystematic because it's errors that are uncorrelated with predictor variables, or at least uncorrelated with the predictor variables that we have in our model. And error is bad in the sense that it reduces power. It makes it difficult for us to detect effects. So I talked about that actually quite a bit in my last lecture. The little black and white picture of the old-timey radio here is just meant as a little bit of a reminder that we can sometimes think about testing hypotheses as a process of tuning into signal amidst noise, so that unsystematic or random error we can think of as like the static on the radio that we hear as we're dialing back and forth trying to tune in on the signal or the effect that we're interested in. So again, one type of error we can think of is unsystematic or random error. And of course, the other type of error is systematic or non-random error. This is error or mistakes that are correlated with variables. Now, they may be variables that we're unaware of. They're confounds that are sort of out there, or they may be variables that we are aware of and might choose to include as additional predictor variables in our model to use that idea of statistical control that we've talked about before. Anyway, the point of systematic error is that it creates situations where we systematically over or underestimate values on the outcome variable for some portion of our data. So for instance, you could imagine, or you could think back to the previous slide where I've got the little scatter plot. Imagine that the x-axis is number of drinks consumed per week. Y-axis is level of depression on the Beck depression inventory. And I'm trying to imagine, or I'm trying to model the relationship between those two variables. To what extent does amount of alcohol consumed predict level of depression? I gather a group of people from a population. I administer some simple questionnaires to measure those two variables, and I create a model. It's just a simple regression looking at whether alcohol use predicts depression. In my data, or when I examine my model, how it performs in that data, I'll obviously see error. It will be the case that my model will miss the data points, at least a little bit, at least most of them. But whether I realize it or not, it's conceivable that I might be overestimating portions of my data and underestimating other portions of my data. So for instance, it might be the case that the relationship between alcohol use and depression is different for men than it is for women. Maybe men drink more than women do. That's actually true based on most available research. And it may be the case that women tend to be more depressed than men, or at least report more symptoms of depression than men. And again, that's probably true based on most available research. So to the extent that I'm trying to look at the relationship between these two variables, in the absence of considering gender, I may tend to, let's say, over-predict depression for women and under-predict it for men, or vice versa. That would be, if that happened, that would be systematic error. I might choose to cope with this problem by only sampling men. That would be experimental or methodological control, or by sampling both men and women but measuring gender, recording gender, and then using that as an additional predictor variable. That would be statistical control. But either way, that that potential problem of systematic error, like unsystematic error, tends to reduce power. All error reduces power. But it can also lead to spurious findings, suggesting effects that aren't really true or don't really work in the population the way I think they do. And that could potentially be a bigger problem. You might draw wrong conclusions if you have systematic error, if you systematically overestimate or underestimate different groups of people. And so this brings us to the idea of bias. Bias is just a type of systematic error, or another term that we could use to refer to systematic error, specifically situations in which systematic error leads us to over or underestimate certain types of folks or certain cases in our data set. So bias can occur because of confounding variables, kind of like I described a little bit earlier with the case of gender as a potential confound in the relationship between alcohol use and depression. Bias can also occur because of problems like outliers in our data set, which draw off or pull off our estimates, or because of violations of some of the assumptions that we make for many of the types of analyses that we do. So in the remainder of this lecture and in the next lecture, I want to focus on this type of bias, this type of problem with systematic error that's associated with either outliers or with violations of assumptions. Let's take a look at outliers first, and this is a bit of a review because obviously we've talked about this before. But outliers, remember, are just extreme values, and in the context of this lecture, they're extreme values that throw off estimates. So for instance, if you have an outlier, in a data set, it'll tend to throw off the mean for that data set. This is something that you probably understand, but we certainly you probably had the experience of being in a large class in college, and there's class mean is, let's say for a test, is an 80%. It's a low B, but really almost everyone in the class scored in the C range, but then that one person aced the exam and it dragged the mean up. It made the mean less of a good description of the data in the sample and potentially less of a good estimate of the data in the population. As we've talked about before, anytime we encounter outliers or suspect that there are outliers in our data, we should probably ask why this is the case. And there are basically two big problems, or two sources of outliers. One might be just bad data. So if we look at a distribution of data that we have for a particular variable and we notice an extreme value, that might lead us to investigate that value, and we might find, oh, there's a mistake in the coding of the data sheet for this particular participant, or there's a mistake in the instrumentation of our recording apparatus for this particular person, or the day we ran this person in the study, Adobe Acrobat decided to update itself, and that slowed down the clock speed of our computer, so it made all our recordings really slow that day. Whatever, bad data. That's one potential source of outliers in data sets. The other source, of course, are legitimately unusual cases. These we can think of as people who sort of shouldn't be in the population or they are not really in the population that we think we're studying. So I think I've used this example before with respect to the counseling center data. It's conceivable that you might have someone in your data set who has a very, very, very low score on the GAF, maybe something like the 20s. Now, assuming that that's not bad data, like it wasn't a mistake that someone wrote 20 when they meant to write 60, maybe that person really is quite low functioning, and in a sense maybe this person shouldn't really be in the population you're studying. This is someone who you're studying college samples, college populations, you're drawing samples from college populations, but this person is really part of like a community outpatient setting and is someone who really would be better thought of as part of a population of mentally ill people in the community. Anyway, it's worth asking always with outliers, why is the person an outlier, and considering these two basic explanations or possibilities. As I've said before in other lectures, and as I probably will continue to say throughout this semester, it's important to deal with outliers. Doing so can prevent a lot of problems, even some of the problems that go along with violated assumptions, which I'll be getting to in this lecture and in the next one. As a really basic idea, I would say if you can deal with outliers, you often save yourself a lot of headaches in a number of different ways down the line. So I think I've expressed this before in previous lectures, and again I probably will, if not in this and future lectures. First look at the data with an eye towards outliers, and if you can address problems there, you probably help yourself a lot more as time goes by. Doing so, dealing with outliers can prevent some problems. Not doing so can lead to lots of problems. At the very least, loss of power, because we have potentially bad estimates of various parameters that we're interested in, and also the possibility of spurious effects or incorrect conclusions based on our analyses. And we'll discuss more of that a little bit later. But for the time being, just note that outliers can lead to bias in estimation, and thus we ought to deal with them if we can. So outliers in our data can lead to bias in estimation for parameters that we're interested in. So can violations of assumptions that we make. What do we mean by this? Well, assumptions are just expectations that we hold about the data that we're using in our analyses. And these assumptions or expectations are necessary in order for the estimation that we're trying to do to work properly. Now, different tests and procedures that we're going to use have different assumptions, and it's important to understand what these are and how the tests behave when these assumptions are violated. Now, if you've taken any amount of stats classes before, you've probably encountered descriptions or lists of the assumptions that go along with regression, or the assumptions that go along with ANOVA, or the assumptions that go along with non-parametric tests, and there are some, and so on and so on. I find these lists sometimes a bit tedious, a bit difficult to learn, and maybe in some respects they kind of miss the whole point, that it's worth understanding what these assumptions are at a rather basic level and seeing how they might play out in the tests that you're conducting. With that in mind, in this lecture and in the following one, I want to present a very general take on the assumptions that accompany many of the tests that we do, or that we will do in this class at least. And in later lectures, when we do regression, ANOVA, and so on, I'll try to return to these assumptions to give more specific examples. Okay, hopefully that'll work for you. The way I think about it, there's some different assumptions, and they can be grouped into two groups. They can be put into two broad groups. There are the assumptions that go along with research design and research methods, things like the assumption of interval data for the outcome variable, or the assumption of independence. And there are some assumptions that are related to data analysis, things like the assumption of normality, or the assumption of homogeneity of variance. what I want to do today, or at least right now, is focus on that first group, the assumptions that go along with research design and research methods. And the first one of these is the assumption of interval data. Specifically, interval data for our outcome variable or our dependent variable. What this means is we assume, or really we should know, that our outcome variable is being measured with such a metric that equal intervals represent equal differences or distances between values. So for instance, if we're measuring something like depression using the Beck depression inventory, we're assuming that there is such a thing as depression that can be measured across a range of possible levels, from rather low or even non-existent depression to rather high or very intense depression. We're not imagining depression as a dichotomous variable which either exists or doesn't exist, or as some sort of ranked variable where there are different ranked values of depression. Rather, we're imagining it as an interval scaling or an interval metric to it. Now this may seem like kind of an obvious point, but actually it's in some ways rather subtle. We might well ask, with respect to a lot of the variables that we use as outcome variables or dependent variables in psychology, whether equal intervals on our supposedly interval metric data represent equal differences. So let's consider the Beck depression inventory, for example. Let's imagine we have 3 people. One person has a score of 10, the other person has a score of 12, and the third person has a score of 14. Is it really true that the second person is more depressed than the first person by the same amount, that the third person is more depressed than the second person? It sort of looks that way if you look at the numbers, but you have to wonder to what extent those numbers, which appear to be a kind of nice sort of well-regulated or well-ordered set of intervals, really map onto the construct at a deeper level. Does depression really scale in that nice even way? And there's certainly some people, especially some people who work in the area of psychometrics, who argue that this is actually really hard to demonstrate in a truthful way. And thus, for our purposes, we often kind of assume, or we are forced to just assume, that that thing we're using as our outcome variable is something that can be measured using an interval scale. And we're also forced to pick outcome variables which have measures that are interval in nature. So if we're trying to predict someone's level of depression from their level of alcohol use, the appropriate choice for our outcome variable is something like the Beck depression inventory or the Hamilton depression inventory, which has a kind of a continuous interval scale. We have to pick that because otherwise we can't really do our research properly. We violated that assumption of interval data. Another interesting point, or really maybe we might almost say an exception, is the case of logistic regression. Now I should say at this point in the semester I'm not honestly sure if I'll cover logistic regression in this class. I sometimes skip it as a topic, not because I don't like it. I think logistic regression is super interesting. I often just run out of time. But suffice it to say, logistic regression is used in situations where we try to predict a dichotomous outcome. So for instance, we might predict whether someone is depressed or not, treating depression as a categorical variable. Now, what I just said seems to run in contradiction to the very thing I said just a few minutes ago, where we assume that depression, let's say, is a variable that has a continuous range that can be measured using an interval scale. In the case of logistic regression, technically what our model is doing is predicting a probability, and that probability is continuous. It just has a function such that it suggests either one outcome at a certain level of probability or another outcome at another. So initially it might seem like our outcome variable is dichotomous in the case of logistic regression, therefore that's a violation of our assumption of interval data for the outcome variable, but in a sense, a deeper sense, it really isn't a violation because we're predicting a probability and that is continuous. Just talking about this makes me think that I really should do that lecture on logistic regression. So hopefully I'll get around to it, and hopefully I'll be able to repeat and maybe clarify this point that I just made. Until then, I'll just note that it's really important at the level of research design and research methods that you think about your measures that you're choosing. So if you're measuring, pardon me, if you're trying to predict depression, let's say, think about how you imagine depression to be. What is the nature of that construct on a deep level? Is it something that is a continuous mood state, or is it something that is a discrete or categorical condition that either exists or does not exist? Now, that's not something you necessarily get to decide on your own. Hopefully you make that decision with respect to the published research in your area, and then you choose a measure of that variable that corresponds to the nature of the construct and is hopefully also a continuous variable, something that would be appropriate for the type of analyses we're going to do for the most part in this class. So again, this is one of those assumptions, the assumption of interval data, that you really it is really just a matter of how you design and how you choose the methods for your study. The second assumption that kind of goes along with research design and research methods is the assumption of independence. Now, the assumption of independence can be a little bit tricky because it means different things in different contexts. One way of thinking about independence is thinking that cases or participants in your study don't influence each other. So the score that I have on the outcome variable in your study isn't influenced by any of the other participants in your study. It may be influenced by variables that you have measured about me, but it's not influenced by variables that you've measured about other people in your study. Another way of thinking about independence is that the errors in the model are uncorrelated. So the amount that the model misses one data point is not related to the amount that the model misses another data point. You might be wondering, why is this important? Well, it's important in different ways. One way is that the mechanism or the mathematical calculations that underlie regression, which we're going to use a lot in this class, are called ordinary least squares, and they're a method for estimating parameters in a model in such a way as to minimize error. So if you make a simple regression to relate level of alcohol use to level of depression, there is one and only one line that can pass through the cloud of dots in your scatter plot if we insist that that line has to be straight or rectilinear, and if we assume that the errors that the model will make will be uncorrelated with one another. If we can't make that assumption, and there are of course situations in which we can't, then ordinary least squares doesn't work to estimate parameters properly. So those regression weights in your regression example will be incorrect. They will be biased in terms of their estimation of population values for those regression weights. So independence is important for different reasons. How do we assess independence or see whether we have violated the assumption of independence? This is one of those ones that's kind of difficult to do. There really aren't good statistical tests that can tell you, oh, you violated the assumption of independence. It's really more a matter of research design. And a question you might ask yourself when you're setting up your study is, to what extent could participants in my study influence one another? Ideally, people come into your laboratory or come into your work area and they fill out questionnaires, they complete computer tasks, and their performance or their level of whatever your outcome variable is influenced by the different predictor variables that you're studying, but is not influenced by the other people who you're also bringing into your laboratory or your workspace. So you could imagine bringing people into your lab and having them all sit around a large table filling out questionnaires. It's conceivable that people might influence each other's behavior or their responses in even very subtle ways, if not telling each other how to answer questions, maybe kind of subtly encouraging people to rush or subtly encouraging people to not take it very seriously. Those could be, again, maybe very subtle effects which would violate the assumption of independence in your data. You might, in anticipation of this potential problem, bring people into your laboratory, but instead of seating them all around a large table, seat them in separate cubicles to do their work. So you minimize the distractions that they face and minimize the extent to which they might influence one another. Perhaps you're having a little bit of difficulty thinking about this. Assumptions of independence can be a little hard to wrap your mind around. So think about the following scenarios and see if it makes sense. Let's imagine you're an educational psychologist studying teaching, and you're doing a simple, fairly simple, experimental design where you're looking at different classes. Different classes in your school are assigned different teaching styles. Maybe one group of classes is assigned to do relatively traditional teaching, just teaching as you always do. Another group of classes are given some new teaching technique, active learning technique or whatever else like that. So in your analysis, your predictor variable is class style, and your outcome variable might quite reasonably be something like student achievement. So the students' test scores on some end of the semester assessment that all the students, regardless of their class or teaching style, will all be taking. Now this seems pretty reasonable, and of course in many ways it is, but there's a potential problem. The students in your data set are each going to have their own row, in your data set. But the students are related to each other because each one is going to be, well, the students in your data set are going to be related, at least some of them, to each other because each of them are in class with other people in your data set. So the extent to which one student does particularly well or particularly poorly in terms of his or her end of the semester achievement is influenced to some extent by the type of teaching style that they were given throughout the semester, but also potentially influenced by the other students in their class. And those students are correlated with each other partly because of their own interactions, but also because they themselves have the same teacher for that one class. So you can think about this like each student isn't an independent data point. They're kind of nested or clumped into class groups. And indeed, if you're going to do analyses for this type of research design, you could, but you'd have to do somewhat more sophisticated analyses than the ones we're going to talk about in this class. For instance, you could do some multi-level modeling where you first analyze the extent to which students' performance is influenced by class, and then the extent to which students' performance is influenced by teaching style that is given to class. Here's another example to consider. Imagine you're a counseling psychologist who studies couples, and you're doing a non-experimental design in which you have couples come into your office, and each member of the couple fills out questionnaires. And you might even imagine that to minimize problems with people influence each other's responses, you have each partner, each member of the couple fill out their questionnaires in a separate room, so they're not talking to each other as they're filling out the questionnaires. Let's imagine your predictor variable is something like personal happiness, and your outcome variable is relationship satisfaction, some sort of score that you can compute from the responses people make on their questionnaire. This may seem pretty reasonable. You might have some sort of hypothesis that people who are more personally happy are more happy in their relationships, or something like that. But there's a potential problem, because kind of like the students in the classes, each individual person is not just, well, independent, but they are related to one other person in your data set. That is the person that they are partnered with, or married with, or coupled off with. So in a sense, each individual is sort of nested in a couple. Now, this doesn't mean you can't do this type of research, but it does mean you have to do some different types of analyses. There's a whole sort of field of applied statistics that's concerned with dyadic analysis, that is looking at or testing hypotheses in pairs of cases, like in this case pairs of coupled people, and you'd have to use those to overcome the problem of the non-independence of people's responses. It's not like you brought 50 independent people into your laboratory or your office and had them all fill out questionnaires separately. You brought 25 couples in, so each of those members of each of those couples is at least related to one other person in your data set. I think I've got one more example here. These are just things I obviously came up with kind of off the top of my head. Imagine you have a health psychologist who's studying cardiophysiology. He or she is doing an experimental design where the participants are put into different exercise groups, and cardiophysiology is measured repeatedly over time. So some people in one treatment group are given a particular type of manipulation, to sort of stress them out, let's say, and people in the other group are given some other manipulation that serves as a control. You could even imagine that these participants are brought into the lab separately, so they're not all like in the same room together. But the important idea is that your outcome variable, whether it's heart rate or carbon dioxide emission, or electrophysiology at the scalp, or so on, is measured repeatedly over time. Your predictor variable might be group or manipulation, and your outcome variable would be physiology over time. The problem here is that each individual is related to him or herself over time. So if you're measuring heart rate repeatedly at 5-minute intervals over a period of time, someone's heart rate at time 2 is related to their heart rate at time 1 and also related to their heart rate at time 3. And there are different ways you might want to handle this non-independence in your data set. So you might do like repeated measures analyses, or you might average each person's score across the whole time period to get rid of that non-independence in your data. Again, the point is, when you're doing analyses, you should think a lot about your outcome variable and think to the ask yourself about the extent to which that variable is independent or non-independent of other cases in the data set. Now, there are some techniques that can be done for assessing independence. One of them that we'll see when we get to regression is the Durbin-Watson test, which looks at the serial independence of errors associated with a model, but it's a pretty limited value, because it just sort of looks at cases which are adjacent to one another to ask if they are or to what extent they are independent or non-independent of another. And so in a sense, it's not a very useful test. It doesn't give us a great sense of the independence or non-independence of data, but it is out there, and we will probably review it at some other point. The point that is maybe more important, or the idea that is maybe more important here, is that there are some assumptions that are more about design and methods of the study than about specific statistical analyses. These assumptions are things like the assumption of interval data and the assumptions of independence. And in order to evaluate the extent to which your particular study has met these assumptions or violated them, you just have to think a little bit about your research design and your research methods. Arguably, you should be thinking about these things anyway, but they are important to think about with respect to these two kind of important assumptions. Okay, review. What have we learned? Well, I talked quite a bit about making and interpreting confidence intervals. And then I somewhat abruptly transitioned to talking a little bit about bias and assumptions. And I focused particularly on assumptions that have to do with research design and research methods. Again, those are the assumption of interval data and the assumption of independence on the outcome variables. Okay, preview. What will we cover next time? Well, I'll be talking more about bias and assumptions now, then focusing more on the assumptions that accompany research data analysis, like the assumption of normality and the assumption of homogeneity of variance. And if you're in my class, I'll be doing a little bit of a review for exam 1. If you're not in my class, of course, you don't need to worry about that, but if you are, just keep in mind that exam 1 is coming up on Thursday of this week coming. Although maybe when you're watching this video, that time will be long since passed, so you maybe don't need to worry about it. But if you do, worry about it. And in any case, thanks for paying attention to my lecture. I know this is a long one. Well, not as long as some of them, but it's getting up there. And so that's good enough reason for me to shut it down right now and tell you that I'll see you next time. Bye-bye.